All right, so I'll start with Moore's Law first. This was a prediction made by Gordon Moore, who's one of the co-founders of Intel, which I'm sure you've heard of as the processor company, regarding the state of processors and predictions and how that market will change in the future. And I'm going to read it first and then explain it. He wrote a whole paper on it. It's very interesting, but this is the main quote that people read. It says, the complexity for minimum component cost has increased at a rate of roughly a factor of 2 per year. It also says, certainly over the short term, this rate can be expected to continue, if not increase. Over the longer term, the rate of increase is a bit more uncertain, although there is not reason to believe it will not remain nearly constant for at least 10 years. This means by 1975, the number of components per integrated circuit for minimum cost will be 65,000. So what does this mean? First of all, components per circuit, those are transistors. Transistors are the building blocks of digital circuits. He made 2 predictions. First of all, his prediction was that the density of transistors in the state-of-the-art, yet economically feasible industry product would double. And his second prediction, or would double every year. His second prediction was that this would continue for 10 years. So it's exponential growth, which means it grows very, very fast. Now let's see how those 2 predictions look on a graph. This is a graph in his paper. It goes to 1965 and then extrapolates all the way to 1975. So let's see how that looks in real life. As you can see, it came pretty close to that. There's 2 main differences between what happened in real life in his paper. First of all, he said that it would double every year. As you see on this graph, this line actually shows every 2 years. So it turned out it didn't double quite as fast as he thought it would, but it's still exponential growth. But secondly, he predicted it would last until 1975. And as you can see, it's gone a lot further than that, and it still has signs going strong 50 years later. Now, I said these are the building blocks of electronic components, but just having the transistors there doesn't make it faster. It's how they're connected to each other that defines how the processor works and whether it's high performance. And so computer engineers have the challenge of figuring out what to do with all these transistors they now have access to. And there's different techniques, and they started with the easy techniques first and moved on to harder ones. And so you get these diminishing returns that are actually very similar, to borrow an analogy from Herb Sutter, to a gold mine, where when they first start mining the gold, it's right there, it's really easy to get, and then they get to the secondary veins, and then they get to the much smaller veins, and the more they pick at it, the harder it is to get, and then at some point there's no more gold that's economically feasible to mine. So here's how that looks. He breaks it into 3 phases. The first phase, this was the mother lode, if you will, the big chunks of gold, were single core processors, which lasted from 1975 till about 2005. And you can see it swings from left to right. The cores get more and more complex. So they added more transistors, and they figured out ways to add them to the processor to make the instructions run faster, both by adding functionality and by just having it go faster. But in 2005, they started running out of ways to do this, both because they had added all the functionality that could be reasonably added, and also they ran into problems with the laws of physics. The speed of light is extremely fast, but in the time it takes a 3 gigahertz processor to complete one cycle, that light only moves about 4 inches. So you can only make it so much faster than that before the electricity just can't get from one point to another. So they still were able to add transistors though, so they thought, well, let's just put in 2 of them. So they moved on to homogeneous multi-core. Homogeneous means they just took the same core, copied it again, and as you can see, there's some components shared between the 2 cores. Also, they have to compete for other resources. Not everything's doubled. And so adding an extra core doesn't double performance, just like adding one person to a one-person team doesn't double the performance. They have to spend some time communicating with each other. But it greatly improves performance. However, this created a new problem for programmers, because in phase 1, they had a bit of a free lunch with their programs, and they could run the same program written in 1975 on 2005 computer, and it would run much faster without having to change the code at all. Because the way programs are written, they're one instruction at a time, operating sequentially. Whereas if you have add an extra core, you have to rewrite your program so that it does 2 things at the same time. And you have to be careful, because some instructions, the order matters. And so if you run one instruction before another, just like if you bake a pan before you put the flour and eggs in, that's just not going to work. So it created new challenges for programmers. And they're still adding more cores. We have 8 and 16 core processors coming out. But they created a new innovation around 2011, heterogeneous cores, which means that the cores are different from each other. So they would add different kinds of cores that were better at different tasks. So for tasks that are designed to be run one at a time, like the recipe we talked about, you want to have some big cores. And then for tasks that can easily be split up into hundreds of different tasks, you have lots of small cores. Other examples of these heterogeneous cores are graphics processing units, digital signal processing. So just have a lot of different types of cores that all do different things. Actually, the PS3 is a good example of this. It uses IBM cell processors that have a lot of different types of cells that let it do things that it couldn't otherwise do with a single processor or heterogeneous, homogeneous cores. But like you might expect, this creates even more challenges for programmers, because not only do they have to split up their tasks, they have to figure out what type of core it'll run best on and designate it as such. So they'd have to say, well, this task will run better on a large fast core, whereas this one, let's split it up and put it on hundreds of smaller cores. And after this, they're, I don't want to say they're running out of ideas, but they're facing even more challenges because, as I said, the longer you go, the harder it becomes to create new innovations. And they've created lots of interesting ways around this. Some of the approaches they're using, you can see here. We already talked about different types of processors. They're also using different memory architectures. Cloud computing is an interesting one because you can pull from resources from other computers. So it's actually not all that dissimilar from having a multi-core processor. It's just the cores are in another room. Some of these other things that you might look into if you're interested in this are reconfigurable computing, analog computing, and quantum computing and nanophotonics. And there's other areas that are new advancements. But having to get extremely high tech to continue this exponential progress that people have come to expect. And so that's the direction that the computing industry has gone in light of Moore's Law. As you can see, technology is getting better, faster, just like Gordon Moore predicted. But the flip side of that is that programmers are having to put in more and more effort to take advantage of these new advances. And computer engineers are having to come up with new and different ideas to actually get these advances to happen. So I thank you for your time, and I'll take questions after this.
Thank you.